then that's fine too. So I'm going to start with going over the different families of the periodic table, just as a reminder of, if we refer to this column, that's what we're saying. But the families are kind of a column. So like the alkali metals, excluding hydrogen, because hydrogen's a non-metal, alkali metals are in the first column. And they're really, really reactive. So reactive, they react with water. I know I in Chem 1 would do a demonstration where I would put sodium metal in water and start a fire on top of the water. You get to see that? Who do you have? He just wasn't prepared to mess with that stuff, huh? I do know the correct amount, because there was a time when I'd used too much, and then one year the beaker that I was in kind of broke because of the explosion due to it. And if you don't do enough, you don't get the fire on the water, so it's just like, okay, I heard a little fizzing, wow, whatever. So you need to know the right amount. Alkali metals, softer metals as well. Alkaline earth metals is the second column of the periodic table. Also fairly reactive, but just not as reactive as the alkali. Again, reason why second column metals aren't as reactive as their first column counterpart deals with ionization energy. That's what we're going to get into. That's more important as we roll into the notes here. Finally, transition metals are in the middle of the periodic table. Those are your d orbital ones. Those are the ones that vary in their number of valence electrons. So what we just looked at was electron configuration. So knowing those slightly different rules, but realizing that every d element almost, I mean, there is an exception. Silver is the one exception I can think of off the top of my head, has a +2 charge because it loses those s electrons first. Excuse me. So hopefully we see, looking at electron configuration stuff prior to this, how the d metals are a little bit different in their electron configurations. And last year in the AP exam, I did see one question that was specifically asking about a metal ion, and you just had to write out the electron configuration. It's meant to be a 20-second question of, hey, do you know you lose the outermost, the s electrons first, which is why most things are a +2. But really, we could use those rules to explain why iron is a +6 ion, dealing with half-filled and full orbitals and things like that as well. So these families here cover the metals. Remember, you start on the left side of the periodic table, you work your way right, you're just metals all the way, excluding hydrogen, and then at some point you hit that staircase. That staircase is the metalloids. So the elements that are on that staircase, above and below, excluding aluminum, are considered metalloids because they have properties of both metals and nonmetals. I mean, if you look at silicone, silicone looks metallic, it's shiny, it's kind of hard, but it also has behaviors of a nonmetal, although it is very good at conducting also. Metal's usually good at conducting heat and electricity. Halogens are the second to last column on the periodic table. They are the most reactive nonmetals. The reason why we don't have a specific family for the carbon column, or the nitrogen column, or the oxygen column, is because as you go down those columns in the periodic table, you cross the staircase. So in other words, oxygen, yeah, that is a nonmetal, but you go far enough down, you hit polonium. Polonium is a metal. So we can't say that they all have the same behavior because some are on the metal-nonmetal border. Again, carbon definitely a nonmetal, but tin definitely a metal. Lead definitely a metal. So we can't say some of those are a family. Now fluorine on down, yeah, those are your halogens. Only family, by the way, that contains all three states of matter. The reason why I bring this up is it's a very common AP question asking why is diatomic fluorine a gas at room temperature, yet diatomic bromine is a liquid, and diatomic iodine is a solid at room temperature. So this gets into what's called intermolecular forces, our next unit. But again, we try to build upon what we've been going over. So I was talking to a group over there that orbital notation we will be using later on in the next unit. So it isn't a learn this, now forget about it type class. Finally, noble gases are the last column in the periodic table. They are the most non-reactive. And why are they non-reactive by and large? Because they have a stable octet. You will learn, however, that noble gases can be forced to react. The ones at the bottom of the periodic table, those are ones that can be forced to react, like xenon, krypton. But then argon, neon, and helium, they won't react. So it just depends on the pressurized situation. So this was meant to be a very brief, it looks like 5 minutes reminder of what are the families. Again, how we use it in AP Chem is just identification purposes. Let's look at the halogens and let's talk about that. You should know what group is the halogens. Am I going to assess you on which family has all 3 states of matter in it? No. But again, when we talk about intermolecular forces next unit, it is a topic that will be brought up. So now let's move on to the trends of the periodic table. The first trend that we always start with, which actually in Chem 1, I'm going over the trends right now, is atomic radius. Atomic radius is really referring to the size of the atom. Now, radius refers to the distance from the nucleus to the outermost electrons. A trend in atomic radius I mentioned with my second and third dash. As you go down a group, atomic radius gets larger. Well, reason for that is as you go down a group, you gain another shell of electrons. That one's pretty straightforward. Again, of all the general trends of the periodic table, which mainly apply to the S and P orbitals, because transition metals are where things get a little weird at times. For all the trends that we go over, as you go down the periodic table, you get bigger. That one is easy for students. What's a little trickier is as you go left to right across the periodic table, the atoms actually get smaller. So as you go from lithium to neon in the second period, lithium has a larger radius than neon does. And in Chem 1, what we went over was the idea that they both have 2 shells of electrons, because they're both in the second row across. However, lithium has 3 positive protons versus neon having 10. There's a greater nuclear charge. There's more positive in the nucleus to attract the electrons to pull them in tighter when we're looking at neon with 10 positive protons and 2 shells versus lithium with 3 positive protons and 2 shells. Something that we really didn't cover as much in Chem 1 would be ionic radius. So what if you're an ion? Just like you guys have to make sure to know how to do electron configuration for ions, especially when you get to the d orbital, losing those s electrons first. In general, an anion is larger than the atom that it came from. If you don't remember, an anion is a negative ion. The prefix an for an means negative. That's going to come up next class as well when we start talking about how batteries are created with anodes. A cation, which a cation is a positive ion. You don't really laugh, do you, Coopens? A grid is something, though, I guess. I'll take it. Is smaller than the atom that it came from. On the very bottom, 2 terms that are often used to describe why things have a larger or smaller radius, either atomic radius or ionic radius, is nuclear charge, which is just referring to your number of protons in your nucleus, and electron cloud repulsion. What I mean by electron cloud repulsion, as you add electrons when you go across a row, putting 2 electrons in the same area are going to want to spread out because they're same charges. Same charges repel one another. So the more electrons you have, the more repulsion you have. The only way they can repel is by moving away from each other and getting a little bit larger. So when I say an anion, a negative ion is larger than its atom. If we envision for a second the fluoride ion. Fluorine is the second shell. Fluoride ion at -1 charge, still the second shell, just gained an electron. The reason why the fluoride ion is bigger than fluorine itself has nothing to do with the positive protons because it's the same number start to finish. By adding another electron, there's more electrons in the same area. And if there's more electrons in the same area and they have all the same negative charge, they repel. They get a little bit further away from one another. So anion's always larger than the atom they came from because of that repulsion. On the other hand, a cation is always smaller. There's a couple ways we can think about that. One is when you take away electrons to be a cation, that means you have less repulsion. Now the electrons don't have to spread out as much, they can be in a little bit tighter. You can also think about the fact that now we have a better ratio of positive protons to negative electrons to attract them. So there's a little bit of both that could be used to explain that one. So again, atomic radius, we went over in Chem 1. Ionic, we might have touched upon, but we really don't do much focus on ionic radius in Chem 1. Electronegativity, probably the most important trend that we use throughout the year of the trends, because it deals with bonding and all other aspects that we have to go over then, whether or not things will be able to mix. And I mean, we covered it a fair amount in Chem 1 as well. Electronegativity is an atom's ability to pull or gain another atom's electrons. The trend is as you go across a period, electronegativity will increase. Remember, as you go left to right across the periodic table, you get smaller. If you're smaller, that means your positive nucleus can reach out and attract a neighbor's electron a little bit easier. As you go down the periodic table, however, you get larger. You have more shells of electrons, sometimes referred to as electron shielding. And if that's the case, it's harder for you now to attract electrons from a neighboring atom. That's why as you go down the group, electronegativity decreases. Can I say nonmetals want a high value? Maybe I shouldn't be using personification for that. Atoms don't have needs and wants and desires. Usually the term that's used is they have a tendency. They want to have high electronegativity. They want to gain to get to that octet, that level of stability. Fluorine, for example, is the highest electronegativity element on the periodic table. It is also the most reactive nonmetal because that. Fluorine will always gain electrons. Again, we go over electronegativity because that will play a role in whether or not there's polar or nonpolar bonds. That's the next unit. But then you'll learn that not only polar and nonpolar bonds, but a molecule as a whole could be polar or nonpolar. You can have something with polar bonds and it's actually a nonpolar molecule. That's something that we have to go over in this level that we don't really cover in Chem 1. So electronegativity, a pretty important trend. The last trend that we talk about then is ionization energy, which I have seen it referred to as electron binding energy, but typically I've seen it referred to as ionization energy. Ionization energy is the exact opposite of electronegativity. If electronegativity is all about gaining electrons, ionization energy is how easy is it to lose electrons. Now here's the thing about ionization energy. It is an actual measured value. And my last slide will go over how we can measure that. Electronegativity is not a measured value. Electronegativity is just a ranking system where fluorine has electronegativity of 4.0. Unless you go to the hundredths place, then they call it 3.98. How they came up with this scale, I don't know. But it's just a ranking system of what's really good at gaining electrons. Ionization energy, on the other hand, is about how much energy is required to lose an electron. In Chem 1, when we talked about ionization energy, we were really referring to the first ionization energy, or it could be called the first ionization potential, which is referring to losing one electron. We didn't really focus on it in Chem 1, but some metals will lose more than one electron. So then there's a value for the second ionization energy. There's a value for the third, the fourth. They probably have documented how much energy is required to lose every single electron within an atom. As you lose more and more electrons, it becomes harder and harder to do. Which is why I mentioned for the last part of this slide so far, more energy is needed to lose the second electron than the first. There's less electron repulsion, so the electrons are closer to the nucleus, so there's more attraction to be overcome. I apologize that I have two more parts of this slide, and that means it's going to get a little bit low. For those of you in the back, you're going to have to stand up and bob your head back and forth. But as for how does electronegativity change as you move throughout the periodic table, as you go left to right across the periodic table, ionization energy increases, just like electronegativity. As you go top to bottom, electronegativity and ionization energy both decrease. The key difference, however, between these two trends is that a low ionization energy is favorable for metals. That means it doesn't take much energy to lose an electron. I mentioned on my last point here that francium is the most reactive metal on the periodic table. It's in the far bottom left-hand corner. Francium is the largest element on our periodic table. When you're large, that means your nucleus is really far away from your valence electrons. And if that's the case, there's not much attraction holding those electrons in. Doesn't take much energy to lose. Smaller elements have a really high ionization energy. Their electrons are tightly held by their nucleus, so it takes a lot of energy to make them be lost. Now, as I said at the start of this slide, this is a measured value. The kilojoules per mole as a unit should be something we're familiar with. We just turned in the lab where hopefully we had that as a unit every now and then. Electronegativity has no unit because it's just a ranking system. So fluorine 4.0, oxygen was at like 3.6. So this is something that can be measured. And my last slide is going to go over one of the ways that this is measured. Again, another difference between Chem 1 and AP Chem is knowing that technique, which is called photoelectron spectroscopy, which is often just abbreviated PES. This is the energy measurement to make electrons be emitted. If you recall from Chem 1, we had students try to remember the steps of how light is created. An electron would gain energy, and it would jump up a certain amount of energy levels, and then would fall back down. And as it fell down, it would give off light. In photoelectron spectroscopy, they can measure the amount of energy that they're putting into an atom. So they know the amount of energy that they're supplying to make the jump. Now think about it. A little bit of a jump, you go up a little bit. Add a little bit more energy, you can go up a little bit higher. Add a little bit more energy, you can go up a little bit higher. If you add enough energy, you can make an electron jump so high that it no longer is attracted to the nucleus at all, and it's just gone. Kind of think about like jumping on the moon. You jump high enough off the moon, you're going to leave its gravitational pull, and man, you are just gone. That's basically what PES does. PES is measuring how much energy can we put into this electron. Okay, jump, it fell. Okay, we gave it a little bit of energy. Let's give it a little bit more and see what happens. And they keep on jacking up the amount of energy until there's enough energy that the electron is gone. And now they have a measured cation there instead. So the steps, hey, let's put in energy, step 1. Step 2, let's get it to an excited state, except we're going to excite it so much that step 3, it's gone. Which is what they would refer to as a photoelectron. Yeah, this is one of the ways they measure ionization energy. Next class, we have to go over this some more. Because one of the points of emphasis that AP put in when they put in their new curriculum is students knowing a little bit about photoelectron spectroscopy. There's graphs that these show that you're going to learn to read next class that demonstrate different peaks, how much energy is lost. Those graphs can be related to the electron configurations of elements that we just wrote out as well. So it is a technique that's used to not only measure ionization energy, but then students can demonstrate their understanding of ionization energy, electron configuration, and then this technique itself, all in one question. And that's the type of things that the AP, the College Board, loves to test students on, is combining things. It's one thing to know, to memorize one thing versus another, but once you start melding things together, that's a higher level of understanding. What we are going to do with the rest of class is we're going to focus on the tread stuff instead. So PES I wanted to introduce today, but we're not going to do anything more with that today. We're going to come back to that next time.